Good afternoon. We are from General Italia, and this talk is about one of the most important challenges that every person that works in a large corporate is going to face at some point, data versus engineer. We are going to present our framework that we have developed over the last few years that want to, let's say, make some order around data we have in the company. Oops. My name is Andrea Purgato. I lead the data platform governance team in General Italia. I moved data since 8 years, and I studied computer science engineering. I'm here with
Federica, and I've been a data engineer for 6 years, and now I'm working in the data platform team at General Italia.
Okay, so let's start. This will be our agenda. We will start with few theoretical slides, I'm sorry. Then we will present our solution with an overall architecture, and we will go with the details with some code. We have recorded a coding session, and we will end by showing how we exploit the Airflow capabilities in order to schedule thousands of different jobs. So let's start by the initial problem. This was the architecture we've had like a couple of years ago. As you can see, it's kind of a mess. A lot of different programming languages, a lot of different technologies, and also the issue about the data management was that they were, let's say, divided in silos, and also the competencies and the know-how on the data were divided in different silos, so there was no cooperation. The results focusing on the data transformation part was that there were a lot of different processes around the company that were reinventing the wheel each time, that there was no monitoring and so on. So let's say that the real issues were, as I said, technological stack not uniform, Wild West feature engineering, so everyone was basically doing what they want without any standard at all, and thousands of different custom processing not monitored and so on. So starting from this, we have thought about four different pillars that we follow during the development of the solution that we are going to see in a while. The first key point was the centralization, because we wanted that different people from different business unit needs to cooperate in order to create a single source of truth, which is the second pillar, because the idea was to create inside our data lake a place where the data are validated by the business owner and the people that have the know-how to validate the data. Then we have, of course, wanted to create a shared technological stack and creating a framework that wanted to reduce the time to production. So data scientist and data engineer does not have to reinvent the wheel, and they can focus on the business logic that is behind the data features. Okay, this is the solution. It's called Efesto, the Generali Data Feature Store. It's embedded in our data lake. As a technological stack, we have adopted Python and PySpark as a programming language and a framework we use to manipulate data. We leverage on Airflow in order to schedule all our jobs. We are Google Cloud native, so we use Google technologies like BigQuery and Dataproc serverless to execute Spark jobs and store data. And we leverage on dbt framework to execute the data quality test. So Efesto is divided in different components. The first one is a Python library called Airflow Common. It's basically an Airflow wrapper that want to expose different DAG builders that are used by other developers to create Airflow DAGs in a standard way. So we as a platform team can manage different DAGs in a central way. To monitoring purposes and so on. Then we have the Efesto core, another Python library that hide all the code that interacts with the data lake, so input output, it standardize it and expose some different classes that are used to implement all the data features. We are going to see in a while in the example how we can do that. Then we have the Efesto features, which is the, let's say, real the main components where all different people from different teams can cooperate in order to define the business logic of the different data features representing business components and business entity. Last but not least, the quality. We have embedded dbt in another Python library that by only writing some configurations, people are able and developers are able to define different data quality checks. Okay, this is a very simplified version of the class diagram of Efesto. The two most important parts are the feature group and the two abstract class. The feature group represent a business entity, like the customer, like the contract, and so on. And the feature instead represents some specific characteristics of the feature group. In practical, a feature is a BigQuery table, and the feature group is a BigQuery dataset. The peculiarity of the feature group is that all the features that belongs to the same group share the primary key. This is because enable data scientists and machine learning engineer to join all the tables, maybe computed at different times, in order to create feature matrices that can be used as input for the different AI model and machine learning models. Okay, theoretical part is ended. Let's get to the example. This is the scenario, very simple. We need to compute two different data features, the fruit cost and grocery shopping, by using three different raw data read from the data lake. The two features, as you can see, depends on each other. And we are gonna see how it is managed, this dependency, at the end of the presentation. Now we are going to see how we need to define, how we use Efesto to define the data features. Okay, first thing to do, define the feature group. The feature group, the first one is the fruits that represent the entity fruit. It extends the feature group abstract class. Some comments, then we need to define the constructor. Here we pass some mandatory variables, which is the composition of the primary key name, some description. Then we move on by defining the fruit feature, fruit cost feature. It extends here also the abstract class feature. We pass the group in order to connect both of them. We pass the scheduling. Now we define a list of tables which are basically the inputs we want to read from the data lake. They are composed by a tuple of strings. The first one represents an alias for the BigQuery dataset. The second, the table name. Now we have some description that is used by the data governance team in order to create and extract some catalog that is exposed in our company data catalog. This is the generate feature method that will contains the business logic. But before defining the business logic, we want to define the unit test in order to approach the problem from a, don't insult me, a test-driven development way. So we want to define before what we expect. In this case, we need, of course, to define which are the different inputs, so the two tables. In order to do this, we need also to create the table schema and the actual data that are inserted into the data frame Spark. The tables have all the same schema, the name of the fruit, the actual cost. Here we're defining the cost. Let's add then the data. In this case, we are adding three different values, apple, banana, and the avocado. We do the same thing for the other input tables, the fruit transportation cost, which is the other cost component of each of our fruits, same schema. We copy the data. In this case, we want to remove the avocado because we hypothesize to use an inner join, so I want to compute the fruit cost only of fruits that appears on both the tables. Then we define which are the expected data. Same thing here. Let's define the schema, which is the same name and cost, and we define what we expect. So the sum of the different fruits that appears on both the input tables. In order to execute the test, here we use a function provided by the Efesto core library. We pass the input, we pass the expected output. We instantiate the feature class and other parameters, and the unit test is ready to be executed. But before, we need to define the business logic. So let's get back to our fruit feature. In this case, we are first reading the input data. As you can see, there is no spark.read.whatever, because Efesto core has already done for us. We have as input a dictionary, the tables, that contains all the data read from the data lake. This is one of the main functionality of the Efesto core, that is hiding the boilerplate code that reads and then that writes the data from and to the data lake. Now we are just joining the two tables. Inner join, we add the cost column by adding the two cost components. What we're going to see now is that we are going to define the feature group related. Sorry, I forgot about the unit test. We are executing the unit test. Of course, it works because it's recorded. Otherwise, we are going to have some issues. Okay. Okay, the test is green. Now let's go with the second data features, the shopping, the grocery shopping. That belongs to another feature group. What's important here is that, okay, the feature group is basically the same as before. What's important is that in the data feature that we see in a few seconds, we create a dependency by setting as input tables the previous fruit cost feature. Now, okay, the description, okay, we have seen this. Let's go with the other data features, grocery shopping, extend features. Okay. Some useful comments. Okay, here you see that we have passed the right feature group, okay, the shopping, the newer one, the scheduling as input table list, input tables. We will pass. The first, it's a row table, okay, as before, tuple of strings. And the second one is the actual object fruit cost. This is useful because when the Airflow DAX is built, he knows that there is a direct dependency, so it guarantees the right order of execution. Okay, moving on. One of the most important functionalities that we have implemented in Efesto is the historicization of the data. This particularity has come from, let's say, as a request from the data scientist. The main challenge is that in the data lake, the raw data, they have no historical data at all. So we came out with a very naive solution. We compute the hash value of all the columns that each feature has. And then for each time we recompute the data feature, we compare the hash value with the latest version, and we keep only the rows that have hash value that has changed. Let's make an example in order to make it easier. Same scenario, production, transportation, and total cost. We have 3 rows in input, orange, lemon, apple, and the result at T0 will be with 3 rows. The hash is different for each row. At T2, what we see is that the cost of the oranges has changed and a new row is added. What Efesto does, it computes the delta by comparing the hash. So a new line with the orange has been written, and the banana, of course, since it's new, it's added to the historic table. At T2, what happens, in order to complicate things, the first row, orange, disappears, so exit, let's say, from the primary key set. The lemon change. What we do here in order to manage also the expiration, okay, lemon is added because, okay, it's changed, but the important thing is that the orange is set. All the columns that has been computed are set to none, in this case just the cost, because time, hash, and expired are technical columns. And the flag expired is set to true. So we know that from that time on, the orange is not going to be in the primary key set. Okay, now Federica will go through the Efesto quality and how we leverage on Airflow in order to schedule all our features.
Okay, now we are ready to write the data quality tests. So we had the aim to avoiding data engineers and data scientists to write code. So we use dbt to implement tests. And dbt needs just a configuration file, a YAML file. And plus this configuration file, we add an environment configuration file. So we can use the same file in all environments that we have. And when we write the file, we deploy on GCP, on GCS bucket, and so that's it. Because our library can read the file from the bucket and manage the test. So we have 3 environments: production, pre-production, and development. And we have an instance of Airflow Composer on every environment with our Airflow Common library. And so also in this case, we have a lot of file of configuration for the DAG construction. And so we deploy this, we put this file on GCS bucket. And our library can create a JKE pod operator for every feature with Dataproc serverless under, so we can manage the server where our Spark job run. And we add functionality to receive on Slack channel some notification if the task failed or succeeded. So this is just the constructor of the DAG builder. So I want to show you this because data engineers that construct a DAG can define some information. And so this is for our business purpose to cluster data. And data engineers can also define the configuration for the Spark job, can test the development branch before going on production, and create for every Efesto feature group, feature group, a slots pool. So in the same group, tasks can run in parallel and in different group. And so the dependency in the Efesto pipeline, we create a metadata file where we define the dependencies. So a task can depend on a task in the same DAG, or can depend on a task from another DAG. And so the DAG builder can manage the dependencies with the metadata file. So I show you just some code. This is the build of the DAG builder, and so we read the metadata file, and for every features that we find in the metadata that belongs to the same scheduling, we create a JKE pod operator with the Dataproc serverless, with all the information that Spark needs to run correctly. And also for every file, quality test file we found in the repository, we create also a JKE pod operator with a Docker container with our code to run the test. And so when data engineers define the DAG, can simply, this is the feature, the quality task we created with a JKE pod operator. And so we manage the dependencies. Okay, when data engineer is ready, can just push the commit on the remote repository, and the pipeline Jenkins starts. Okay, and so you can find a lot of steps just to validate what we are doing, and if we are in a development environment, we create a sandbox, we deploy a sandbox, and in this sandbox we find just the DAG that we have created or we are modified, not all the tasks in production. Okay. So this is the DAG. You can find some technical task, and as you can see, there is a fruit cost task that is the feature that we created with Andrea before, and we have defined the quality for the fruit cost feature. So after the task of the feature, we have the task of quality, and the shopping grocery feature that depends on fruit cost feature depends on its quality. Okay, so if the quality failed, the task of the feature, the grocery shopping doesn't run. Okay, when the DAG stops to run, we can find in BigQuery 3 tables. So an historical table, a latest table with, for each primary key, the latest row, and a snapshot table that is the data from the last run, just the data from the last run. Okay, this is BigQuery, and you can see the data set, and this is the historical table with all the data. And so fruit cost latest is the latest table and the snapshot from the last run, data from the last run. And also quality puts some information in a table in BigQuery with information about the test, so if the test failed, how many rows failed, and some other information that we use in data governance to monitoring quality of the data. To monitor. Okay, just few numbers. And so we deploy in production our library 2 years ago. And in these 2 years, more than 70 developers use the tool. And more than 400 features have been created in 18 DAGs. And these features use 100K hours per month in CPU time. Okay. Thank you.
So thank you for the talk. We have time for question on slide, or we already have some question. Okay. Okay, I start with a shorter one.
Okay.
What about the vertical lineage of feature? Is it pushed to a lineage backend?
What do you mean with vertical lineage?
Okay, I think there is someone that asked from online.
From online?
Okay. Let's go with the next one.
Okay, let's.
It's better. Have you considered buying commercial solutions like Tecton, Opsworks? Why in the end did you decide to build your own?
Okay, good question. We have evaluated a few years ago solution from the market. The reason was that at that point they were not really ready for our use case, I think. Not because the library was not, let's say, capable of, but since we have a lot of peculiarities that are how our company is organized, it was difficult to implement those solutions from the market. So we have opted to implement our own solution. in this way, we let's say could tailor the solution on our needs. This was basically the idea behind.
Okay, we have another question. It's a bit longer.
Okay.
Are the features used only for analytical purpose and for training ML model, or are they also used for inference, like when predicting a price on the website?
Okay. Data features are used mostly to as an input for the training for machine learning models. Sometimes happens also that inference is computed on Efesto. It's not quite common because the idea is that everything that come out from Efesto should be something meaningful for a specific business case, respecting the concept of entity and feature. So if I'm putting something that is very specific for my business case, maybe it's not useful because since the feature store is shared among different legal entity of the company, if I'm putting only my data that has meaning to me, I'm just let me just pass that I'm creating noise around the data features. So all the models are managed outside of Efesto. This is basically what we do.
Okay, we have other questions. I don't know if they are for Federica. Why did you call it Efesto?
No idea.
Okay, the next one is, what's your favorite part of Efesto?
Wait, Efesto is the Greek god of engineering, if I'm right. So it's like we are engineering data.
It's your product. Yeah. don't ask me. Okay, I was reading. What's your favorite part of Efesto?
Difficult to say. I guess creating something that standardized all the data transformation part where we had a lot of entropy. In this way, now we have a very specific central solution used by a lot of people. So, I mean, this is not from a technical point of view, but we have simplified lives of our colleagues. So I think we are happy about that.
Okay. So we don't have any time to answer other question, and in 2 minutes there will start the break, so you can go downside and have some
Thank
food.
you very much.
Thank you.